Hi all of you. Welcome to another lecture of antenna and wave propagation. The topics for discussion today is the structure of atmosphere and the skywave propagation. Myself Maria Joseph, Assistant Professor in Electronics and Communication Engineering Department of MBC CET Pyramid, leading the session. Structure of atmosphere. This is the basic structure of atmosphere. An atmosphere consists of troposphere, ionosphere and an outer atmosphere above 400 kilometers. You have a troposphere is here, then you have a stratosphere, then you have an ionosphere, then the outer atmosphere. Please learn this diagram. It may be asked for the exam. Structure of atmosphere. Since the medium between the transmitting and receiving antenna plays an important role, it is necessary to study the medium above the earth through which the radio wave propagates. The first layer, the troposphere, the structure, it is that portion of Earth's atmosphere which from Earth's surface extends up to a height of 8 to 10 km at polar latitude, 10 to 12 km at moderate latitude and 16 to 18 km at the equator. On an average, it has a height of 15 kilometers. The actual height is at the poles and the maximum is at the equator. Although the gas components remain constant with increase in height, the water vapor components sharply decrease with height. The structure of ionosphere, that is, we have different layers for the ionosphere. That is the D layer, E layer, F1 layer, F2 layer and the G region, that is the outermost region. D layer, it exists between 50 to 90 km above Earth's atmosphere. It's a daytime phenomenon and largely absent in night, the travel of the radio waves in this layer. At low frequencies, the space between D layer and the ground acts as a huge waveguide, making communications possible. The next one is the E layer. It exists between 9 to 140 km above Earth's surface with maximum density at 110 km or 110 kilometers. It is almost constant with seasonal variations. This layer permits medium distance communication in low frequency and high frequency bands. The next layer is the F1 layer. It exists between 150 to 200 km above Earth's surface in summer and 150 to 300 km in winter. This layer is almost constant with seasonal variations. Next is the F2 layer. It exists between 250 to 400 kilometers. At night, the F1 layer slightly rises and F2 layer slightly lowers. To form one layer, it is called as the together F1 plus F2. It is called as the F1 layer. These regions are also called as the Appleton regions. The G region, which is the outermost layer, that is the region above 400 km, is known as the G region. It consists of charged particles trapped by terrestrial magnetic fields. The second topic for discussion is the skywave propagation. Propagation of ground and space waves are limited by the curvature of Earth. We know that the Earth is round in shape and it is having a curvature. So there are big limitations for the ground and space wave communication. The propagation over long distances are performed by skywaves. They are reflected by ionized regions of atmosphere and returned back to Earth in single hop or multiple hops. Hop means, suppose you are transmitting a signal with a single reflection from the atmosphere back to Earth, then it is called a single hop. And if it is if you are transmitting by falling it on Earth once and then again transmitting it to the atmosphere and finally it falls on the receiver, then it is called a multiple hop. Okay. Now we have one derivation. I've written it as in form of a note because it will be easy for you, because this is a frequently asked question. The expression for finding the refractive index of ionosphere. In an ionized medium having free electrons and the ions pass through, it is set these charged particles in motion. The radio wave passing through the ionosphere is influenced by the electrons and the electric field, and so on. You can go through the reasons why we need to learn the derivation. The reduction in the dielectric constant due to the presence of electrons in the ionosphere causes the path of radio waves to bend towards the Earth. So since there are electric ions and electrons present in the atmosphere, they will bend the signal back to the Earth. Let electric field across the cubic meter of space in the ionosphere is given by E is equal to Em sin omega t. The force exerted F is equal to minus E into E. Assume that there is no collision occurring. So we can say F is equal to mass into acceleration minus E into E. That is equal to m dV by dt. dV by dt is equal to minus EE by m, or dV by dt is equal to minus EE by m into dt. I hope till this you will understand fast, because it's a basic logic things, simple maths. Okay, the second part of the derivation. Fine. That is integrating. You got integrating dV is equal to minus EE by m into dt. That is V is equal to E by m omega into Em cos omega t. We get V is equal to this value after integrating. Now we have to find out the current. That is, if capital N be the number of electrons per cubic meter, then the instantaneous electric current is given by I is equal to minus N into E into small letter v, where capital N is the number of electrons, E is the charge of electron, and v is the velocity. I is equal to minus N into E into v. We have already found what is v, and so we get the current I as this value. One more current is there, that is a capacity or the displacement current. That is, it is given by IC is equal to K0 Em cos omega t into omega, where K0 is found to be a constant. Now IE, total I. Total I is the sum of IE plus IC. So you add these both equations, that is IE plus IC will give you this equation. Okay, K0 Em omega into cos omega t minus N into E square by m omega Em cos omega t. Now I is equal to, we take Em cos omega t into omega outside, you get K0 minus N E square divided by m omega. So that is equation 2. Suppose you are comparing these two equations, we get K is equal to, we will get one value K, that is K is a constant, and K0 minus N E square by m omega square. Comparing equations 1 and 2, we'll get a equation, because we know that this much of things Em cos omega t into omega is found to be same in both the equations. So you can take one letter K is equal to K0 minus N E square by m omega square. Fine. Then K is equal to K0 minus N E square by m omega square. So you have K is equal to K0 into 1 minus, suppose you can take K0 outside, K is equal to K0 into 1 minus N E square by m omega square into K0. So you can say the relative dielectric constant is given by Kr is equal to K divided by K0. That is 1 minus N E square divided by m omega square K0. Fine. So we can find out the value of refractive index, that is root of Kr, that is root of the relative dielectric constant will give you the value of mu. Understood? So how will you find the value of mu from this equation? That is, we know that capital N is found to be the number of electrons. Then what is M? M is actually 9.1 into 10 raised to minus 31 kilogram. That is the mass of electron. Omega, you can turn this into 2 pi f. Okay, and K0 value is 8.854 into 10 raised to minus 12. So substituting all these values, you get the value of mu as root of 1 minus 81n divided by f square. This is comparatively an easy derivation, but it's a frequently asked question, so you have to learn this. Fine. Then if you're looking at this is the text from which I've took this derivation. and these topics. So you can refer both of them. And thank you so much for your patient listening. Thank you.